Okay, in this podcast I'm going to solve those 4 problems that were in the packet. Okay, so the first one says, find the Kc if 0.1 molar of both H2 and I2 are present initially and 0.134 molar of Hi is present at equilibrium. Okay, so our ice table has H2, I2 becoming 2Hi. My ICE, it says initially I have 0.100 molar of each of these. And my assumption is I start with no Hi. Okay. So what it also tells me is at equilibrium, let me just draw some lines here, is that at equilibrium I have 0.134 molar of the product. Okay. So if I assume I'm losing some amount x of each of these because they have the same coefficient and gaining 2x of the product, I can use this to figure out what x is, right? So I have 2x equals, 0.134 molar. So x is going to be 0.067. So if I take 0.10 minus 0.067, which x is, that's going to give me 0.033 here. Same thing here, 0.033. So my equilibrium expression is Kc is equal to the product, 0.134 squared, right, because there's the 2 here, over 0.033 for the H2 and 0.033 for the I2. And if I plug and chug, I end up getting a Kc of 16.5 equals my Kc. Okay, let's try the next one. What value is the Kc for the decomposition of ammonium carbamate if the equilibrium concentrations of the products are these? Okay, so I'm just going to put my ICE under this. Alright, so what I have here is, it says my equilibrium concentrations are 0.212 and 0.106. Now I'm going to assume I start with no product, right? And that I gain 2x of this, and I gain x of this. But wait a second, if I look at this, this is a solid. It does not go in the equilibrium expression. So all I need for my Kc is going to be my products raised to their coefficients. So it's 0.212 for NH3 squared times 0.106, which is the concentration of CO2, and that's raised to the 1. Key thing here is that this is all goes over 1 because this is a solid and its concentration will not change appreciably. So I end up, if I plug and chug, I get 0.00476 as my Kc. Okay, let's take a look at the next one. Alright, given that I have concentration of A of 0.15, concentration of B is 0.225. These are both at equilibrium. What is C at equilibrium? Okay, so let's take a look at that. So my Kc is given to me. My concentration of A and B at equilibrium are given to me. So my expression is Kc, which is 2.61, is equal to, let me see, the concentration of C squared over the concentration of A and B. So I can rearrange this and say the concentration of C squared equals 2.61 times the concentration of A times the concentration of B, right? Because I'm just cross multiplying here. And if I do that, it's 2.61 times A, which is 0.15 molar, and B is 0.225 molar. And what I get is C squared is 0.08809. So C is going to be the square root of 0.08809, or 0.297. Alright, one more here. A reaction vessel contains N2O5 with an initial concentration of 1 molar. If N2O5 decomposes to form NO2 and O2, what concentration of those are present at equilibrium? And you're given a hint to write a balanced equation. So if I'm going to go from N2O5 to NO2 and O2, let me see, so I'm going to need 2 N's, but this is an odd number, so I'm going to need to double this. So I'll end up with 4 of these, and now I have 4 N's, but I have 10, so that's going to be balanced. Okay, so my ICE, alright, initial concentration of 1.00 molar of this, alright, and I want to know what concentrations of NO2 and O2 are present at equilibrium if the N2O5 at equilibrium is 0.268. Okay, so let's think about what we have here. So, I'm assuming that we're going to start with no product, right? And if I use my coefficients, I'm going to lose 2x here, gain 4x here, and gain 1x, right, based on the coefficients. So I can use this to find x. So 1 minus 2x is equal to 0.268. So my x is going to be 0.366. Okay, so I'm looking for my equilibrium concentration, so x is 0.366, so it's going to be 0.366 for O2 here, and it's going to be 4 times 0.366 for NO2, and that is going to be 1.46. And these are molar, right? And this is for NO2. All right, and that's going to do it.